I'd like to invite the next young investigator to the stage. So we have Scott Tavernini from the University of Alberta. Scott is a research engineer and a PhD student in Canada, working in the Aerosol Research Laboratory of Alberta, and he's going to tell us all about his research today.
Thank you very much for that introduction, and thank you for the opportunity to be here today. It's my pleasure to present to you the most recent progress we've made using our regional deposition in vitro apparatus, and that's to use that apparatus to get some satisfactory pharmacokinetic estimates. Because pharmacokinetic modeling is based on accurate regional deposition modeling, I want to start off today with a brief description of making these estimates with existing tools before we get into the longer discussion of the considerable effort we've taken over the last half-decade to develop this regional deposition device. And then we'll get into a comparison of the PK estimates arising from both methods. So the long way of getting to these regional deposition estimates, I call it the long way, using existing tools. It's a quite involved process. So it's well established now that to get a in vitro lung dose that is accurate or close to what we expect to see in vivo, you need to use an accurate extrathoracic model, as well as test, especially for DPIs, with a relevant inhalation profile. If you do this, then your lung dose that's characterized in an impactor can be used as input to a regional deposition model. The model we use at the Aerosol Research Lab of Alberta provides regional deposition estimates on a generational basis. And these estimates then can be used as input into your PK model down the line. But this is a very complex process, and the experiments themselves are quite time-consuming to conduct. So we were hoping to find a faster way to do this. And the idea then is to put some sort of a dose collection system downstream of the extrathoracic airway. And if that system can remove the tracheobronchial dose, including, of course, the appropriate dependence on inhalation flow rate and particle size, most strongly affecting deposition of aerosols, then that will leave the alveolar dose behind for collection later on. We wanted this to be very simple to use, to work with constant flow rates, which will simplify PMDI testing, but as well to work directly with realistic inhalation profile, simplifying DPI testing. So then all you need to do is use a quantitative assay to get to your regional deposition estimates from the collection system. So in order to achieve this, we settled on a filter-based approach, which required us to develop a very specific filter. It's kind of a bad filter, actually, in the sense of filters. Most filters are collecting a lot of the dose, and this one's collecting a very small amount, but a specific amount. So we specified using a predictive model, a two-layer filter design that we see some micrographs of the filter elements here. The wire diameters and the opening spaces here on the scale of 25 to 30 microns, so they're quite fine. But with this filter specified, then we validated it through some physical measurements of oil droplet aerosol. And so in the panels here, we have measured under tidal flow rate with an average of 15, 30, 57, and 81 liters a minute in the 4 panels. And the red series that we see is the measured filtration of the filter relative to a number of different in vivo and in silico average tracheobronchial estimates. So seeing some really good agreement between our measured filtration efficiencies and estimated tracheobronchial deposition, especially at the higher flow rates where we expect single-dose inhalers like DPIs and PMDIs to be tested. We were really satisfied with this, that we'd found our filter element, and we wanted to move on to integrating this with use with extrathoracic airway and inhalers. But this isn't as simple as just putting it downstream of the AIT. There's a couple physical effects that we needed to deal with. And we ended up going to this annular shaped housing to deal with these physical effects, and one of those being non-uniform flow through the filter. So the laryngeal jet that exists coming out of the AIT, it impacts on the top of this annular core here. So this core here impacts the jet that's coming in, and then the flow comes down relatively uniform through the annular section. And this is important to match the filtration efficiency that we've seen in the last slide that was so carefully developed. Additionally, the electrostatic charge on the particles can cause artificially high filtration this is our TB filter down here. Because the length scales are so small, about 20 times smaller than the most distal generation of the trachobronchial region. So the annular shape allows a ring on the outside here to ionize the air, and then as the particles come through the annulus, they're neutralized and then are exposed to the TB filter. The dose getting through the TB filter then is collected on an outlet filter, which, based on all of the careful design of the filters, should be representative of the alveolar dose, under the assumption of no exhaled dose, of course. So that's our quick way system, where we're getting our regional deposition in vitro, but not without validation. So we did a number of head-to-head comparisons between for 4 DPIs and 3 PMDIs using the long way with the cascade impactor, and then the new regional in vitro quick way. So the blue series shown here are the long way estimates, and the orange being the quick way, and the darker series, or like the left of each 4, are the trachobronchial estimates. Notice that the graph on the right has a much higher y-axis limit, and this is capturing the high alveolar estimate for QVAR, which it has a very small residual particle size and a low momentum plume. But what we see here is really good agreement between the 2 methods. We're really happy to see this and see that the general trend is captured for a number of different products, different flow rates. So we took this to mean that the regional deposition estimates are in agreement. But the regional deposition estimates are only the starting point for the longer process of disposition of drug in the body. And with our kind of 2-compartment deposition, that fits very naturally into a 2-lung compartment model. As one we see here, where the regional deposition estimates go into our solid, undissolved compartment, where then they are subject to a dissolution rate into the free compartment, where then their uptake to the central compartment can happen. But in the trachobronchial region, this is in competition with clearance by the mucociliary, or mucociliary clearance into the GI tract. And for us, that was the biggest question, is what is the mucociliary clearance for this model? And we wanted to compare this simple model to a more complex one, such as the one here, developed by Martin and Finley, where when you use the long wave and you have generational estimates of deposition, each generation can be its own compartment with mucociliary clearance defined by an airway surface liquid model. So we wanted to collapse this large process into one. And using this larger model, previous work in our lab by Rizicki et al. Showed very good agreement between some in vivo studies and estimates using that large model. So we see here their estimates are the solid curves and the in vivo data overlaid. So the question was, what do we use for our mucociliary clearance rate in the 2-lung compartment model? And we selected this by matching the trachobronchial clearance between the larger model and our simple model, just by manually playing with that mucociliary clearance rate. All the other PK model parameters were previously selected by Rizicki et al. Based on work by Weber and Hawkes. So by selecting a rate of 0.45 per hour, we see very similar clearance. So we selected that and can continue on to the PK model output, which is what we see here. The green series, the TB model, the less complex model, in really good agreement with the longer the long way approach generational model. Despite the relative simplicity of the quick way method and model, the estimates are in very close agreement. So we're really happy to see this agreement. It's a simple model, simple method, but at least for budesonide. There's a lot more actives out there. We'd like to look at like further dissolution limited actives. Something we're working on. As well, we see a lot of potential to further develop the whole in vitro method with the tracheobronchial and alveolar doses now separated into their own collections. We'd like to be able to maybe measure the dissolution rates so that we can help parameterize the model with the dissolution rates right in there if we can measure them with a physiologically relevant dissolution test. And this is active work that we are doing in our lab right now. So before we get to some questions, just a quick thanks, deep appreciation to my supervisor, Dr. Andrew Martin, for his continued support, as well as Dr. Warren Finley. Dino Farina is our collaborator. He's been instrumental in this project, as well as Preveris Scientific for their generous funding that has made this a reality from an idea. And thank you for your attention.